Hey guys, probability, yeah, cool. Um, so okay, we're gonna talk about probability in this video, right? Yeah, in fact, the whole chapter is probability. Of course, you know that. There are a couple of words that I think it's important that we know what they mean and what they are. So yeah, for the first I don't know for the first how long, but for the first couple of minutes in the video, I'll just be talking and then I'll start writing. Yeah, as time goes by. So, you know, the whole idea of probability, even the word probability itself, it's just saying the likelihood of something happening. If we talk about the likelihood of something happening, we're talking about its probability. Do you know what I mean? um, and quite often we use probability a lot when we are talking. Yeah, we may not even use the numbers to say a probability like this, but we use it quite often. You know, just a good example would be like friends are going out, and you ask about someone. You know what I'm saying? Good example. Say for example, you guys are going out, of course, like I said, and one of you guys ask, you guys, is Nsani going to be with us today? Is he coming, right? And based on the data you guys have, like he barely show up for such things. So the answer, and also you're not sure if he will come again. Most of the time he doesn't show up, but sometimes he does show up, and there's no way of telling whether he is gonna show up or not. So what you will just say is probably not, right? You are not saying he's not coming, but there's just a higher chance of him not coming based on your previous, experience. Another good example was you guys know like that one person who's always late. It doesn't matter what you guys, say or do, but you know that whenever there's something to happen, your guy is going to be late no matter what, right? And there, like, if someone actually then ask, right, you'd be like, most probably he's gonna be late, right? And yes, there are times when he arrives early, but most of the time he's late. So just say most probably they will be late, right? It's just you using probability, yeah, to just have a conversation about how likely something is to happen. So on the words, we have the first one is an experiment, which an experiment it's something you perform, right? Something that you do to test a particular thing, right? Good example, you want to see which students actually passes maths, or perhaps you want to see, say for example, with the students that actually pass maths, you are checking variables like do they have money at home? Yeah, well, because sometimes it does happen that when like families with much more money, their students tend to not care much about school, right? And you would only find those with little to no money being the one who like, for now you need to go to school, you need to make us proud, this is that, so that could be one of the variables you guys are checking. Does money, right? Does a family having money have an impact on how the kid perform, right? Because even on the contrary, someone can say, no, but like families with no money to little money to no money, most of their kids tend to be criminals and be very disruptive kids. Yeah, when they're always late at school, always causing trouble at school, and so forth and so forth and so forth. Perhaps one of the reason is they've already gave up long time ago, or they don't see even the point of going to school. So like there are just many variables. So you don't know if whether is money causing the children not to want to perform much, or is not having money at home the reason why people, is poverty the reason people don't. Yeah, well, so you don't know what actually happens. So you perform an experiment. You will take kids, who have lots of money from home, kids with not a lot of money from home, and you run multiple tests, make them write tests, ask them questions. You are making an experiment, right? And then the result that is going to um, the results which you're going to get after the experiment, we call that an outcome. What is the outcome of the experiment? No, we found out that apparently majority of the kids from rich families, they tend to perform very well because they have a lot of resources. Or they started learning these things when they were kids. Whereas on the other side, those with families with no money, they don't have resources to learn these things at an early age, and therefore they struggle as time goes by. You know what I'm saying? Finding it hard. There are just so many. Right? So whatever it is that you will find, we call that an outcome, to say, this is an outcome of our experiment. And then sample space. So sample space is a thing of in the experiment that you are performing, how many, what's the proper word to use? Okay, I'll use this one. It's not a proper word to use, but yeah, it brings us closer. The total number of people that you have that you'll be making your experiment on, right? Yeah, say for example, you take 20 kids from rich families and 20 kids from poor families, to make that experiment. You want to make it fair, so you took 20 from rich, 20 from poor. You combine them. The sample space for that experiment is going to be 40, which is the total number of people, who the experiment is being on, right? And of course, the event is an event is something that will actually occur, right? Good example, like, yeah, you could find out that this is a possible event, that kids from poor families, they work much harder than kids from rich families. They just want to make it out of this life. Yeah, they are tired. Yeah, it's not nice to be poor, and they don't love it. And yeah. Or another event is this one is not an event, but yeah. Another thing you could find out, maybe children from poor families, right? They are more motivated than children from rich families. It's another possible event. So it's like you will see also with the examples that we're going to do, right? When we talk about an event happening, yeah, I think, here's another good scenario that explains an event. You have a die, a fair die, right? And by a fair die, we're simply saying you have six sides, a six-sided die. So with that die, of course, it has numbers 1, 2, 3, 4, 5, 6, right? And you can roll a die and you will get a particular number facing up, right? So getting 1 is an event. Getting even numbers is an event. Getting prime numbers is a possible event, right? So yeah, now when we when we name our probability, you see here probability and there's an arrow. We say probability is equals to what? The number of events possible divided by the number of the sample space. The S is for sample space, right? So how many people, not how many people, like the sample space, like, yeah, how many events are there? Oh, beautiful thing. How many events are there? That's the sample space, right? How many events are there? And then the numerator is the number of events that occurred. For example, you roll a die, right? No, you don't roll a die, but with a die we ask a question: what is the probability of getting an even number, right? So you're like, in a die, how many even numbers do you have? You have 3, 2, 4, 6, right? So then you will say number of events, which is number of even numbers, that is 3, over sample space, right? Number of sample space. So you have not number of sample space, but yeah, you have 6 possible numbers. So then the probability becomes 3 over 6, right? And with that being said, there are these two concepts, that is theoretical probability and relative frequency there. So theoretical probability on it, so there's like logic to it, there's some mathematical what the words are not coming, but like, you see, for theoretical probability, what this formula that we have here, that is us using theoretical probability to find the probability of things actually happening. Yeah, well, like there are formulas that we use to say, okay, here's a formula, right? And it doesn't change. It's always like that. Good example, a coin. It can land on head or tail, right? And we know that there's a 50-50, there's a 50% chance of either, right, of a coin landing on either head or tail, right? So with that being the case, you know that, say for example, a head, if I spin a coin, probability of me getting a head is 1 over 2, which is 50%, right? And it will always be like that. It will always be like that. But for relative frequency is like, we perform an experiment. So we take a coin and we're gonna twist it 100 times. Ne? 1, 2, every time we flip it, we record the result to say, oh, it landed on head, tail, head, tail, 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 head, tail, 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 head, right? Yeah, that is that. So the thing also with relative frequency, it's when you have flipped the coin 100 times, and now you have recorded your results, you can find out that you got head 37 times, right? And you got tail 63 times, right? That would mean the probability of a head, it was 37 over 100, which is 0.37. And the probability of a tail is 0.663, right? So that is relative frequency, right? That is relative frequency, which you see that it differs from theoretical probability, because for theoretical probability, we know possibilities there of getting head is 50% and getting a tail is 50%. Do you understand? Yeah. So, and for relative frequency, you would do like many trials. The many trials you do, the more accurate your results will be. And the more accurate your results will be. So I'm done talking now. I'm gonna write a couple of stuffs and we're gonna solve a couple of problems together. Yeah. Just stay with me. Cool stuff. So we are saying even numbers from 2 to 100, right, are written down on a card, on cards. Now, even numbers. What is the probability of selecting a multiple of 5 if the card is drawn at random? Ne? Cool. So I can make it. Let me. I will make it long. Ne? So first and first, you need to find all your possible events, which is all possible even numbers between 2 and 100. So you have 2, 4, 6. I'll pause the video and finish them. Cool. So I have, these are all even numbers between 2 and 100. And these even numbers, I need to check now how many of them. Okay, let me check my NS, right, which is my sample space. So I'm checking how many they are, right, how many even numbers I have. So I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So I made sure that they are properly aligned. So this is 15, this is 30, this is 45. 45, right? 45, 45, 45, 46, 47, 48, 49, 50. So I have 50 possible even numbers, right? All these even numbers between 2 and 100, that is 50 of them in total. So now I need to find the probability of selecting a multiple of 5 if a card is drawn at random. So now I need to find what NE is, right? And NE, remember I said, is the number of possible events. So we're gonna look for those events, even numbers that are divisible by 5. So 5, 10, 15, 20, 25, 30, 35, 40, right? So it's gonna be 10, 20, 30, right? And then 40, 50, 60, 70, 80, 90, and 100. You see? So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That means we have 10 of them. Let's count again just to make sure. This is 3, this is 6, 7, 8, 9, 10. Right? So therefore, probability, right, of this event, which is, I'll just say E for event, bro. I don't want to write long things here. And E, number of events, and S, right, which is 10 over 50, which is 1 over 2. No, over 5. I think that's 0.2. 1 over 5. That is 0.2, right? So we did find the probability. Let's do another example. They say a playing card is selected randomly from a pack of 52 cards. So these are your cards, the one we use for ball crazy aids, 5 game, 5 cards whatsoever. Those cards, there are 52 of them. Determine the probability that it is, right? So let's go for A. We know we have I'll just say NS is 52, right? Because in total we have 52 cards. Now we're gonna have to find an E for each of these. They say, what is the probability that card selected is the 2 of hearts. So now how many 2 do we have in our cards? We have 4 2s, ne? It's a 2 of spade, 2 of a fly, 2 of a die, 2 of a heart, right? But now the question is, they want the card to be 2 of hearts. That means you know that there's only one 2 of hearts, and therefore the probability is going to be an E and S, which is going to be 1 over 52. You can put it in a calculator to get a decimal answer if you want. Actually, let us do it. 1 over 52, and it's 0.019, right? 1 2, which is 1.2, 1.2. No. Yeah, 1.2%. Yeah. Let's see. Then B they say probability of us getting a red card. So remember now, a red card, we are talking about what? We are talking about your diamond, right? Diamond or a dice, or and hearts. They are the two that are red, right? And that is going to be half of the 52. So 52 divided by 2, it's 26. So there are 26 of them. You can think of it like this. We start with ace, ne? Let's say we are talking about hearts, ne? We have ace 2 3, ace 2 3 4 5 6 7 8 9 10, and then king, queen, jack. So there are 13 of them. And then you go to die, there are 13 of them as well. Combined it's 26, right? 26. Therefore your probability here is going to be, it's going to be what, 26 divided by 52, right? 26, 52. I'm sure it's gonna be 1 over 4. Oh yes it did. Wait, what? Oh, not 1 over 4, 1 over 5, bro. Not 1 over 5, 1 over 2, which is a half. Oh, come on. So 0 0.5, right? Let's go for C. A picture card. So a picture card, look, that's king, queen, jack, right? There are 3 of them per a group of cards. I don't know, pair, whatever. Yeah, so it's gonna be 3 times 4, because we have a die, heart, we have a fly, and we have a spade. So 3 times 4, that is 12. So and in number of possible events, 12. Therefore your probability of that event will be that'll be 12 over 52, right? So 12 over 52, you're getting 0 0.23. Maybe I can put 1. All right. Cool stuff. Then they say we did a picture and then an ace, ne? For an ace, so how many aces do we have? We have a 1 ace per I don't know what these things are called, like, yeah, like the 4 of them, like spade, like, yeah, but we have 4, we have 1 ace per cards, so that's gonna be 4. It's gonna be 4 over 52, right? You can write it in a decimal form. I'm not gonna. And then a number less than 4. A number less than 4, they didn't say equal, so we're not gonna include it. So that is 3, that is 2, that is 1, right? And 1, of course, that is ace. But this one also, I don't know, it will depend on, right, how you guys consider it. I know we sometimes call it 1, other people they say it's 11, right? Other people they say it's like 40. So hey bro, like different people actually play this thing of cards different ways. There are many rules, but I'm gonna count it in, I'm gonna call ace to be 1, so I will include it. So that means there are 3 per 4. So I'm like, so it's just gonna be 3 times 4, which is 12. So therefore here it will be 12 over 52. Right, let's see what we have here. Yeah, so here it's a beautiful question. They say a die is tossed how many times? It is tossed 54 times and it lands 5 times on the number 3. So here this is us doing that relative frequency. You have many trials, right? Tossing that die, right? You're tossing that die, tossing it. You did it, you tossed it 42 times and you got 5. Yeah, oh, it lands 5 times, so you got 3 5 times. You got 3 5 times. Now the question is, what is the relative frequency of observing a die land on the number 3? Right, so it's very simple. You got 3 how many times? 5 times. Therefore the relative frequency there is going to be 3 over 44. The reason we are saying 44 is because you oh no 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 no. Cool. Let me erase this gag. So there's something we need to think about first, something we need to consider first, right? Remember, remember, in probabilities, we must first think of what? Wait. We must think of this thing called like a die itself. It has its own probability, and getting 3 when you roll a die, probabilities of or chances of you getting a 3 when you roll a die, it's of course 1 over 6. Yeah, 1 over 6. 1 over 6 is the probability of you getting what? Getting a 3, right? So how are we going to attack this question, right? How are we going to attack it? Because now it's like there's 44 1 over 6s, because the probability of getting a 3 from a die is always 1 over 6. But now this is a question that clearly puts the what can I say? This is a question that clearly differentiates between theoretical probability and relative frequency. So remember, the 1 over 6, that is the probability, that is the theoretical probability, that 1 over 6. Ne? But when we do the relative frequency, we do a thing multiple times, right? We run multiple trials. Like here we did it 44 times. We rolled the die 44 times, and we only got 5 times. So that means to do this one, we use relative frequency and actually say 5 over 44, which is basically the number of times we got it. 5 over 44, and that is 0.11, right? Yeah, this is it. And perhaps what can I say cool. But yeah, this is something that really helps us get the difference between a relative frequency and theoretical frequency. If we used theoretical frequency, it would have been 1 over 6, which is 1.16666, or 0.17, which differs from this probability by 0.06. Yeah. Cool. Do I have? Cool. Oh, cool. Yeah. So here's another person. So a die is tossed 30 times. So, oh no, you take a coin. You toss it 30 times, and it lands 17 times on heads. Now, what is the relative frequency? Relative frequency of observing a coin lands on head. It's gonna be 17 over 30, right? Which is 17 over 30, which is 0.566, quite close to the theoretical probability of 0.5. 0.5, right? Yeah, my light just went off. So if this is another examples of probabilities, let's just chart them quick. So you have this diagram with ages, gender as well, right? It's cool. And we have like 3 people, of course, here. Oh no, we don't have 3 people. They say if a child is selected at random, what is the probability that the child will be, right? So before you could get to that, you need to find out how many children do we have here. So see, for 3-year-old people, we have 2 males and 6 females. So here the number is 8. For 4-year-olds, 5 males, 7 males, 5 ladies. So you add the 2, that is 12. 6 and 10, 6 and 4, that is 10, right? And then you add all of these, 8 plus 12, that is 20. 20 plus 10, that is 30. So you have 30, which is what? NS, right? That is your sample space. And now the question is probability that a kid will be a female. So you go to the female sides, you add all these numbers, 6 plus 5 plus 4 divided by 30, which is gonna be, that is 10, that is 15, 15 over 30, which is 0.5. Yeah, and then here probability that the child is a 4-year-old male. How many 4-year-old males do we have? We have 7 of them, so probability becomes 7 over 30, which is 7 over 30, that is 0.23, right? And then here probability that you have kid aged 3 or 4, right? So aged 3 or 4. So this one is going to be the probability that you have a kid who is aged 3, which is 8 over 30, plus probability that you have a kid aged 4, which is 12 over 30, and that is 20 over 30, which is 2 over 3, and I think that's 0.67. Yeah, 0.67. And then so this one, probability that a child is aged 3 and 4, this one is impossible. There's no way one person can have 2 ages, unless people are confused about when the kid was born. But one kid can only have 1 age. There's no way I can be 25 years old and be 26 years old, right? No way. So here probability is 0, and I haven't mentioned this. When we say probability is 0, we basically say it can never happen, right? It can never happen. Good example, probability. What is a probability that a white man, yeah, a white man and a white lady make a black kid? Probability are 0 unless there was a black man involved, right? Yeah, so here they say probability, yeah, okay. Oh, what is the probability that a child will not be 5? So a child is not 5 years old. That means a child is either 3 years or 4 years. It's going to be the same probability here of 0.67, because it's going to be probability that they are 3, which is this, probability that they are 4, which is this. Adding them together, you get this, and you get this, which is this. Right? And then here we have either a female, or either 3 or a female. So probabilities that they are 3 years old is that probability of them being 3-year old, that is 8 over 30. Or the probability of them being female, here it's 15 over 30. You add the 2, you get 23 over 30, and yeah, 23 over 30 gives you what? 7.00000. What did I say? 7.666. Yeah, 7.6666. All right. Let's jump to these questions. Yeah. So for these questions, you have what do you have? A box containing colored blocks. So you have colored blocks. The number of each color is given in the following table. So yeah, so a block is selected randomly. What is the probability that the block will be? No. Probability that a block will be purple. This is how you do it. For purple, you're like, okay, how many purple blocks do I have? You have 24. Therefore, N and E is 24, right? And then NS, what's NS? NS is adding all of these together. So we'll do that in a calculator. That is 24 plus 32 plus 41 plus 19. That is 116. So 116. Ne? That is NS. Therefore, probability of purple, probability of that event happening, it will be 24 over 116, right? You can punch it and say 24 over 116, see what you get. 0.2, if you do it to two decimal place, that will be 0.21. all right, yeah, 0.21. Purple or white, it will be probability of getting purple, which is 24 over 116, plus probability of getting white, which is 41 over 116, which is 65 over 116, which is 65 116 0.56. all right, and then pink and pink and orange, right? So that one is going to be 0, because when you select when you take out a block, right, you take out one block at random, there is no way you could get a block with two colors. Yeah, so and here if we say pink or white, yeah, but we're basically saying it doesn't matter so long as the thing that you picked was purple or white, right? So long as it was purple or white, that's why we then add the probability of the two: probability of white, probability of purple. And then they say not orange here, so that will mean we're gonna it's there. If they say no orange, we are saying it could be purple, it could be white, it could be pink, and therefore the probability will be 24 over 116 plus 41 over 116 plus 19 over 116. You add all of these, you get your answer. So you have 24 plus 41 plus 19 divided by 116. The answer is 0.72, and just like that, you are done. All right. Yeah, so I'll see you in the next video. Yeah, I'll see you guys in the next video. Awe.